Good day, my name is Ringgau. I'm from Department of Electrical Engineering, Polytechnic Mekah, Malaysia. I'm here to talk about the electrical power production of a small-scale hydrokinetic turbine. If you are interested in this study, please contact me at my email address ringgau@gmail.com. This is the outline of my presentation today. So first, I will talk briefly about the introduction, which includes problem statement and objective, and then research methodology, result, and discussion. At last, I will summarize the findings in conclusion. What is hydrokinetic turbine, or also known as HKT? HKT is one of the technology in renewable energy. The HKT converts the kinetic energy of flowing river into mechanical power. The generator then turns the mechanical strength, which is harnessed by the rotor, into electrical power. Why electrical power production is important in HAHT system? The electrical power production can be used to aid in site model calibration, reference source for optimum performance of a HAHT system, and validation of numerical prediction of an identical system. How to estimate the power production in HAHT? We can use software and simulation design tools such as TurboGAN and CFD. However, the result frequently higher than experimental or the output speed, and tend to overestimate the operating point. Besides, to validate the numerical model and gain insight into the performance of the HKT, we need to do laboratory scale testing, which is the facility there is no or limited towing tank or circulating current flow facilities to perform the test in local universities or in Sarawak. Therefore, to overcome the overestimating operating point in software production and no towing tank of recirculating current flow facility, the combination of theoretical and laboratory experiment are proposed. Therefore, this study involves the following objective. First, to estimate the tip-speed ratio, coefficient power from this CPTSR performance curve of HHT system. Second, to estimate the maximum turbine rotation speed, or MT, according to the river velocity, nu, and at the right TSR. Third, to identify the maximum and typical generator rotation speed, NG, according to the nu. And then to plot the prediction graph based on the output current produced by the generator as the function of the rotation speed. To verify the performance of the prediction graph by comparing it with the measurement data from the field site. To estimate the optimal tips ratio, or TSR, and coefficient power, we need to plot a CP-TSR performance curve of the HAHT system. So if you see here, equation 1 is the power coefficient equation, where theta is a pitch angle. So a pitch angle is the angle between the rotor plane and the blade tip skirt. So lambda, or tip speed ratio, or TSR, is a ratio between the tangential speed of a tip speed of a blade and the actual speed of current water. For this case, a rotor fixed pitch angle was 15 degrees, which leads to CV versus lambda characteristic shown in figure 2. From the plotted graph, we found that at maximum coefficient power, TSR was between 4.8 until 5.1, but to simplify our calculation, the value of TSR was 5. To estimate the maximum turbine rotation speed, NP, equation 2 was used. This equation shows that the relationship of PM, Cp, and river velocity, where alpha is the swept area of the turbine, which is 2.25 meters square. Rho is the function of fluid density, and nu is the velocity of river. The drain train efficiency is 88%, which consists of generator and gear ratio efficiency. Equation 4 was derived by using the definition of TSR by inserting the value of TSR and the diameter of rotor. This formula was used to estimate the HAHT rotation speed and velocity at the river at optimal operation. The relationship of HT and NG were established from the transmission gear ratio used in the system because it amplified the rotational speed of the generator energy by using 90-degree transmission gear with ratio 1.75 ratio. Therefore, equation 5 was derived and then maximum rotation speed was identified. For method, we divide it into two parts: laboratory experiment and field experiment. All experiments were under control variable. In laboratory experiment, the load conditional test was performed on a PMDC motor. The experiment setup was shown in figure 4. The VT or generated voltage was maintained within the 12 volt with 5% tolerance. RL or load resistance was made from 9 pieces of 12 volt DC LED in a parallel form, and a switch is connected in series with each pieces of LED bulb. Then a switch was turned on to connect the load resistance with the output terminal of generator. A resistance of 16 volt is built up. If two were turned on, then 8 volt was connected to the output terminal of the generator. The resistance was continuously decreased until the switches were turned on. So 9 measurement was recorded and repeated 3 times. So the HAHT system was fabricated and deployed at Sungai Sarawak, Kiri, Sarawak. The experiment was observed under flow condition of 1.2 meter per second. The real-time operation was measured and recorded by a data logger, filter, and then undergo data treatment. For result and discussion part, figure 6 shows the laboratory setup together with a voltmeter, current clamper, digital tachometer for load condition test. 9 measurements were recorded and presented in figure 7. Figure 7 indicates that the output current and the generator power were proportional to the rotation speed of the generator. The linear graph of the output power and current as a function of rotation speed of the generator had R-squared value of 0.9965 and 0.9966 respectively. This indicates that there was a strong agreement in the relationship between the recorded measurements. Figure 8 was plotted based on Figure 7. Figure 7 was extrapolated until the rotational speed of the generator reached its limit at 378 RPM. Minimum rotation speed of generator current is 119 RPM at river velocity 0.7 meter per second. The HKT system export energy when the river has reached enough amount of velocity to transfer its kinetic energy into the turbine rotor, or in other words, when the turbine has exceeded its cut-in speed. The field side measurement data was filtered and selected from lambda value, which were around 4.8 to 5.1. After data treatment, we compared the prediction graph with the measurement data from the field site, shown in figure 9. The prediction graph should be as close as possible to the observed or actual data. Mean absolute error was chosen because it was a suitable method to solve the issue that are related with the measurement of the river velocity might not be possible accurate due to position of sensor or transducer must be very close to distant to the rotor. This issue was important because the HAHT power curve ideally correlated velocity with the river. So from here we found out that the power mean absolute error was 16%. Whereas for the prediction graph of NG, it only suffered from 5% of mean absolute error. As for conclusion, the aim of this research was to identify the predictive line of HAHT energy for 12-volt electrical system appliance suitable for a lowland river or channel with a low power rate. The performance of the prediction graph was compared with measurement data from field site. The graph was slightly consistent with the trend seen in the actual measurement value within the range of river velocity around 0.8 to 1.4 meter per second. The prediction data, or PG and NG, was suffered 16% and 5% of absolute error percentage respectively. Even though the performer require the the functional specification of a wind power forecasting system reported by State Grid Corporation of China, the MAE of the predictive value of 4 hours should be less than 50%. The electrical power prediction was considered plausible, whereas for prediction graph of MG, the performance was within the standard, which indicates that the predictive line is accurately close to the actual data. So the design HAHT system was a courtesy of Dr. Tan Keng Wei and Dr. R. Martin Anyi. So here's the references using this study.